Okay, thank you for listening. My name is Miguel Ángel Domínguez. And this talk is called Improving Search Efficiency and Diversity of Solutions in Multi-Objective Binary Optimization by using Metaheuristics plus Integer Linear Programming, by me and my supervisors, Francisco Chicano and Enrique Alba. In the introduction, I'll start with the introduction and the background with the necessary definitions to understand the work. After explaining our proposed algorithm, which is called MoFels, I'll finish with the computational experiments and the conclusions. We are in the context of multi-objective optimization with binary variables. We want to design a hybrid algorithm which can take the advantages of exact algorithms and also the advantages of metaheuristics. The algorithm should be designed spreading solution of the objective space as best as possible, and also it should can handle any number of linear constraints. The idea is to use an ILP solver just to get a feasible solution, and then we do a local search with delta evaluation. To do this, we adapt a framework to solve multi-objective combinatorial optimization problems. And finally, we assess the results using 5 metrics and 28 instances, comparing our algorithm MoFels with the metaheuristics NSGA2, SPA2, and MOEAD. In this slide, we can see the definition of a binary linear multi-objective program using matrices. We can see here an example for 2 objectives, 5 variables, and 3 constraints. We say that a vector X dominates another vector Y if each component of X is less or equal than its corresponding component of Y, and at least one of the inequalities is strict. We say that a feasible solution is efficient if its image is not dominated by any other image for any other feasible solution. And the image of the set of all efficient solutions is called Pareto Front. We define a p-dimensional box as a generalization of a cuboid or a hyperrectangle. A box can be defined by its lower bound and by its upper bound. In this work, we use only lower bound to calculate the volume of the box. It will be fixed during the execution, and it will be a lower bound for the ideal point. The upper bound sets or fixes the region to explore in the objective space. Our work is based in this framework developed by Dacher and Klamroth. In this, we can see this easy algorithm to calculate the complete Pareto Front. It consists in selecting regions to explore or boxes, solve the corresponding model in line 5, and if a new solution is found, we add it to the Pareto Front and update the corresponding set of boxes, and if not, we eliminate that box. Line 9, you can see it. The updating procedure, we use the same updating procedure in our algorithm, consists in split some boxes into new boxes, eliminating the region dominated by the last solution found, and also eliminating the redundant boxes. We will see this with an illustrative example later. This is our proposed algorithm called MoFels. This is the pseudocode. It is divided in 3 main parts. The first part is the initialization. We initialize the Pareto Front and the set of boxes as the empty set. In line 3, we need to define a delta vector which consists on a small positive values, because in line 8, when we solve the model, the inequality, the constraints used by the ILP solver are of type less or equal, greater or equal. So because of the quality and in order to avoid repeated solutions, we need to subtract a small positive value. In the second part, we calculate a lower bound and an upper bound for the Pareto Front using linear relaxation. The lower bound will be fixed during the execution, and it's a lower bound for the ideal point. In the third part, we are exploring, we are in a loop while there is at least one box to analyze and another stopping condition is given. And we order the boxes in a non-decreasing way by its volume. With this, we achieve a very good spread over the objective space. We use in line 8 the ILP solver just to get the feasible solution, and then in line 11 we do the high climbing. The filter function in line 12 consists in eliminating all dominated solutions during the execution, and the updating procedure is the same as commented before. For instance, suppose we have that bi-objective model with 3 constraints, and the ILP solver gives us the feasible solution 11001. Then in line 10, we calculate the slack vector, which consists for each constraint of the difference between the right-hand side value and the left-hand side value. And we do the local search calling the high climbing function. This is more or less how it works. Now we're going to see inside this third part, the mathematical model. The mathematical model combines a parameterization of the objective functions and the epsilon constraint method. Because the ILP solver is used only to get a feasible solution, the weights of the objective functions are not very important, and we set those of them to the value 1. Here we have an example for 3 objectives and an initial box, 8 for 3. On the right, we can see the parameterization of the objective functions, and we add 3 new constraints, 1 per objective functions, and in the right-hand side, we have the corresponding component for the box. Now we see the local search. This is the pseudocode for the local search. We're going to see this with an example. For instance, suppose we have the same model as before, the same example. That's the parameterization of the objective functions. And the feasible solution given by the ILP solver is 11001. We evaluate the objective function, which is 3 in this case. Then we evaluate the constraints to calculate the slack vector, which is the difference between the right-hand side value and the left-hand side value. And now we do we check if flipping any variable, we can improve the solution. First, we start with the 5th variable. Observe that if we, I don't know, I can annotate. If we flip this bit, we will improve in 2 units the objective function. So we can check the constraints, and if we flip the bit, we can see the variations on the slack vector here. But the solution is not valid because the 3rd component must be 0 because it's an equality constraint. The slack vector should be non-negative values for less or equal constraints, non-positive values for greater or equal constraints, and must be 0 for equality constraints. So in this case, we do not accept this solution. Now we check the fourth variable. In this case, if we flip this variable, the objective function will increase, so we are not going to improve the solution, and we reject also this flip. Suppose now we select the second variable. In this case, if we flip the variable, we will improve in 1 unit. And when we check the constraints, we obtain this variation and a valid new slack vector. So finally, we have an improved solution by flipping the second variable. We update the objective value by its new value and the slack vector. And we repeat it again, this process, until no improvement in the neighborhood is found. Finally, we're going to say the updating procedure and how we split the boxes of the regions to explore. Suppose we have the initial box defined by its upper bound, 10, 10, 10. We select one box. In this case, we select the only box we have. And we have the feasible solution 462. Then we split this box into 3 new boxes, B1, B2, and B3. Observe in the picture that the region dominated by the last solution is discarded. Now we select next box, for instance, B1, and suppose that this region is empty. There is no solution in that region. So we discard it and we select the next one. Suppose this is B2, and we obtain the solution 552. We split this box into 3 new boxes, B4, B5, and B6. But in this case, we can observe that box B6 is dominated by box B3, which means that each solution found by B6 can be also found by B3. So B6 is redundant, and we can eliminate that box. Then we select next box and continue with the algorithm. Now we are going to continue by showing the instances. We have selected 28 instances. 10 of them are for the multi-objective assignment problems. 10 of them are for the multi-objective knapsack problem, and 8 of them are for the multi-objective, multidimensional knapsack problems. The references for the benchmark are given below. We have marked in bold those instances for which we know the complete Pareto Front. And this is good when interpreting the results because we are more accurate, because we have the complete fronts. The metrics used in the experiments are the number of solutions, the hypervolume, also the hypervolume ratio, the generational distance, the inverted generational distance, and the epsilon additive indicator. We need to maximize the number of solutions at the hypervolume. We need to minimize the other 3 metrics. Before executing the algorithm, we need to tune the corresponding parameters using the iris package. For our algorithm of else, we only have one parameter, which is an upper bound for the ILP solver to get a feasible solution. In this case, iris gives us the value 0.4 seconds. For the rest of the parameters, the configuration given by iris for the Metaheuristics are given in table 1. In table 2, we can see the computational results for the instances for which we know the complete front. We run 30 times each instance during 30 seconds and take average values. We can see in bold the best results. We can observe that most of the best results are given by Morphel's. We can only see that neither of the Metaheuristics can find any solutions for the assignment problem. This is because this type of problems has only equality constraints and it's very difficult for the metaheuristics to find any feasible solution. On the other hand, MoFels can find near 100 solutions on average because thanks to the ILP solver, because we get the feasible solution and we do only the local search to improve the solution. In this table, we can see the results for the instances for which we don't know the complete Pareto front. Now the reference set is the union of all the sets given by the experiments plus an external computation during 40 minutes. This is done for each instance. We can see again that, most of the best results are given by MoFels, which are marked in bold, and we have also good results for MOEAD in some cases. In this table, we have calculated the hypervolume ratio for those instances for which we know the complete front. I think these are very good results because in only 30 seconds of execution, we can achieve about the 85% of the total hypervolume for the assignment problems and about 99% of the total hypervolume for the knapsack problems. We can see also that the IGD values for the assignment problems are very close to 0, which means that the approximative front are very close to the real Pareto front. In this graph, we can see an example for the multi-objective assignment problem with 10 agents, only 100 variables. And we can see in blue the complete front, and in red, the approximating front using MoFels in only 5 seconds. We can see that with only 5 seconds of executions, the approximative front is well spread and apparently very close to the true Pareto front. In conclusions, we have presented, a hybrid algorithm to solve binary linear constraint multi-objective problems. And the results are quite good using the 5 metrics in only 30 seconds of execution. According to these metrics, the solutions are well spread over the objective space. And remark that the use of constraints is a handicap by using metaheuristics in general. But with MoFels and thanks to the ILP solver, we avoid this drawback. For future work, we would like to compare MoFels with other Metaheuristics and also extend the research, if possible, to nonlinear functions. And we would like also to analyze the behavior of MoFels as time progresses. And that's all. Thank you very much for your attention. And if you have any questions.
Okay, thank you so much, Miguel Ángel. Monique Skirtino asked in the chat a question, and later we can make another question. Okay. So she asked, in the local search procedure, which order do you follow to flip the bits?
Sorry, I can't see. Sorry, wait a moment, please.
Yeah.
I can see.
Worry.
I have a technical problem. Can you see my presentation?
Yeah.
Yeah. So I'm not. I can see. I don't know what the problem is. Well, never mind. Can you repeat the question, please?
Yeah. In the local search procedure, which order do you follow to flip in the bits?
Okay, random search.
Okay. Okay.